We're about to embark together on a journey, a quiet voyage, not just to the very edge of time, but then we shall take a step beyond its confines. Our destination is the ultimate mystery, the question that underpins all other questions, the query that reverberates through the very fabric of our understanding. What precisely was there before the Big Bang? Allow that question to simply hang in the air for a moment, not as a challenge demanding an immediate definitive answer, but rather as a soft, persistent hum, a cosmic mantra perhaps, resonating deep within our consciousness. There is no need to grasp for a ready solution, for the greatest minds throughout the entire tapestry of human history have themselves only ever been able to offer whispers and tantalizing echoes of potential explanations. Our purpose this evening, then, is not to unearth a final, incontrovertible truth, but simply to listen intently to those whispers, to trace the path of those echoes, and to allow the sheer, humbling scale of the question itself to lull us, to draw us gently into a state of profound, serene contemplation. The journey we are about to undertake is not one of rigid facts and cold, hard figures, but rather a journey of monumental ideas, magnificent, soaring concepts that stretch the very weave of our imagination to its absolute breaking point. So, if you haven't already done so, perhaps just close your eyes for a moment. Take a slow, deep breath, filling your lungs right to their very base, and as you exhale, simply release any lingering vestiges of tension. And now, let us begin our silent wandering into the time before time. The story with which we are all perhaps most intimately familiar is that of the Big Bang itself. It's the grand narrative of a single, utterly unique moment, an instantaneous genesis that unfolded approximately 13 8/10 billion years ago. In that infinitesimal fraction of a second, everything, and I mean absolutely everything, all of space, all of time, all matter, and indeed all energy, erupted outwards from a point of unimaginable, almost infinite density and heat. It is a powerful, exquisitely elegant story, one that is supported by an absolutely staggering weight of empirical evidence. We can perceive, even now, how the galaxies are hurtling away from one another, much like ships departing from a bustling central port, a direct, undeniable consequence of that primordial expansion. And we have, quite remarkably, detected the faint residual afterglow of that initial cosmic fire, the cosmic microwave background radiation, which bathes the entire celestial sphere, a kind of ancient photograph, if you like, of the infant universe itself. But our restless, inquisitive minds, even when relaxed into this meditative state, quite naturally begin to pose the question, what then ignited the fuse? What preceded that singular, awe-inspiring moment? If the universe truly had a beginning, what was the inherent nature of the state from which it began? What if, by simply asking the question, we are already reaching beyond what the universe permits us to perceive? For a very, very long time, this question itself was considered to lie firmly beyond the very frontiers of science, relegated to the realms of philosophy or even faith. Science, after all, concerns itself with what can be measured and what can be tested, and how, one might reasonably ask, can one possibly measure that which existed before time itself? But as our understanding of physics deepened, so too did our audacity, our sheer intellectual courage, to ask such profoundly unsettling questions. And the first set of ideas that we might explore are those that attempted to circumvent that thorny, intractable problem of a definitive beginning altogether. These are the classical and semi-classical alternatives, born from a deep-seated desire to posit a universe that was, in some meaningful sense, eternal. A universe, you could say, without a birth certificate. Imagine, if you will, a cosmos that possessed no moment of creation. A universe that had simply always been, and would always continue to be. This was the central bedrock idea behind the steady-state model, a theory elegantly proposed in the mid-20th century by astronomers Hermann Bonde, Thomas Gold, and most famously Fred Hoyle. It was a vision, of profound, almost serene stability. In this model, the universe does indeed expand, precisely as our observations so clearly demonstrate. We perceive galaxies receding from us, and the vast spaces between them stretching ever wider. But, from the perspective of the steady-state model, this does not imply that the universe was ever smaller, or indeed denser. Instead, as galaxies drift apart, creating increasingly wide voids, new matter is continuously and spontaneously brought into existence within that very void. This creation, it must be stressed, is not some dramatic, explosive event, but rather a slow, gentle, almost imperceptible process. One solitary hydrogen atom might appear here, another there, scattered across unimaginable stretches of space and time. Precisely enough, over aeons, to condense into new dust, new stars, and eventually new galaxies. This ceaseless process ensures that the overall density of the universe remains utterly constant. An observer, positioned at any moment in time and at any location within the cosmos, would perceive precisely the same, unchanging cosmic panorama. The universe, in this captivating vision, is eternally self-sustaining. It is a cosmic ocean that continuously expands, yet whose water level, as it were, always remains perfectly the same, fed by some unseen internal wellspring. This idea, known as the perfect cosmological principle, was deeply, profoundly appealing to its proponents, precisely because it circumvented what they perceived as the philosophical difficulty of a singular creation event. Hoyle, in particular, found the notion of the universe having a definite beginning inherently unscientific, a form of pseudoscience, he felt, that too closely resembled ancient religious creation myths. It was Hoyle, in fact, who sarcastically coined the very term Big Bang during a BBC radio broadcast in 1949, specifically to express his profound disdain for the rival theory. He intended the name to sound dismissive, to underscore what he considered its irrational, unphysical nature. Ironically, the catchy name stuck, and the very theory he sought to ridicule went on to become the cornerstone of modern cosmology. The steady-state model was, by all accounts, an elegant and philosophically pristine construct, presenting a cosmos that was eternally consistent. However, every beautiful idea in science must, ultimately, pass through the crucible of observational evidence. The eventual downfall of the steady-state model came with a discovery that was, in its own remarkable way, a revelation of the universe's own memory. In the 1960s, two physicists, Arno Penzias and Robert Wilson, whilst working with a large horn antenna at Bell Laboratories, detected a faint, persistent microwave hiss emanating from all directions of the sky. Initially, they attributed it to interference from New York City, then to some supposed defect in their equipment, and even meticulously cleaned pigeon droppings from the antenna, suspecting them to be the source of the unwanted noise. But the hiss simply refused to vanish. It was precisely the same day and night throughout every season of the year. It was a uniform low-energy glow, an ancient light that had travelled for billions of years. This, it turned out, was the cosmic microwave background radiation, the unmistakable echo of a time when the universe was incredibly hot, astonishingly dense, and undeniably young. It was the reverberating whisper of a primordial fireball. The steady-state universe, having never been in a hot, dense state, possessed no mechanism, no explanation whatsoever for this all-pervasive warmth. The cosmic microwave background was a photograph of the universe's infancy, proving unequivocally that it had an infancy. The universe had not always been as it is now. It possessed a history, a narrative arc. And with that faint, persistent cosmic hiss, the elegant idea of a stationary, unchanging state faded gently into the annals of scientific thought, a beautiful but ultimately incorrect picture of our cosmos. But could there truly be a cosmos without a birth certificate? And yet, the yearning for an eternal universe did not simply disappear. It merely transformed. If the universe could not be eternally the same, perhaps it could be eternally cyclical. This gave rise to the grand idea of the oscillating, or cyclical, universe. Allow your mind to settle into the image of a great cosmic breath. The Big Bang in this framework was not a singular beginning, but rather just one exhalation in an infinite series. In this model, the universe expands after a Big Bang, driven by that initial explosive energy. Galaxies form, stars shine, perhaps life even arises, and over billions upon billions of years the cosmos grows ever larger, colder, and darker. But gravity, that silent, patient force that inexorably draws all matter together, never sleeps. If there is sufficient matter in the universe, more than a certain critical density, its collective gravitational attraction will eventually overcome the expansion. The cosmic tide will turn. The expansion will slow, halt, and then reverse into a contraction. This would be the Great Contraction or the Big Crunch, a Big Bang played in reverse. Galaxies would cease their outward flight and begin to rush back towards each other, slowly at first, then with accelerating, unstoppable momentum. The universe would grow ever hotter and denser, rewinding its stages in reverse. Stars would merge, galaxies would collide, and eventually all space, matter, and energy would collapse back into an infinitesimally small, infinitely hot point, a singularity, precisely like the one from which everything began. And from this crucible of cosmic renewal, a new Big Bang would erupt, birthing a new universe, a fresh expansion, a brand new cycle. The universe, in this captivating vision, becomes a cosmic phoenix, eternally regenerating itself from the ashes of its own demise. This profound idea boasts ancient philosophical roots, but in the 20th century, physicists such as Richard Tolman gave it rigorous mathematical scrutiny. He showed, however, that these simple cyclical models ran into a critical, almost insurmountable problem, rooted in the second law of thermodynamics. This fundamental law dictates that entropy, a measure of disorder or randomness in a system, can only ever increase. With each cycle of expansion and contraction, the universe would inevitably generate more entropy, more waste heat, more disorder, more radiation. This accumulating entropy would render each subsequent cycle longer and larger than the one before it. If extrapolated backward in time, the cycles would have to be progressively shorter and smaller, ultimately terminating in a very first unique Big Bang, precisely the very thing the model was attempting to avoid. The cycles, it seemed, could not truly be eternal. For many decades, this entropy problem appeared utterly insurmountable, and the oscillating universe model faded into the background. However, the astonishing discovery of dark energy in the late 20th century, a mysterious force that appears to be causing the expansion of our universe to accelerate rather than slow down, has reinvigorated interest in cyclical models, albeit in a new, far more sophisticated form. Modern versions, such as those proposed by Paul Steinhardt and Neil Turok, incorporate concepts from M-theory and brain cosmology, ideas we will delve into a little later. They propose a mechanism where the universe traverses endless cycles of expansion and contraction, but the temperature and density remain finite at the point of transition, thus gracefully sidestepping the destructive singularity and resolving the problematic issue of entropy. In these models, the bang is more accurately a bounce, and our current era of accelerating expansion, driven by dark energy, is a natural, perhaps even essential, part of the cycle, setting the stage for the next contraction, which might occur trillions of years hence. Building upon this concept of a pre-existing state, a more modern and highly refined idea has emerged from the strange, almost ethereal world of quantum gravity. This is the hypothesis of the Big Bounce. It shares a kinship with the oscillating universe in that it postulates a phase of contraction prior to our current expansion. But crucially, it resolves the vexing problem of the singularity, that point of infinite density where the very laws of physics simply cease to function, by means of a quantum mechanical trick. In the bizarre realm of quantum mechanics, the very fabric of space-time is not a smooth, continuous sheet. At the smallest conceivable scales, the Planck scale, it is believed to be grainy, composed of discrete, indivisible units, much like a digital image is made up of individual pixels. What if the universe, in its ultimate densification, simply refused to be crushed out of existence? According to theories such as loop quantum cosmology, you simply cannot compress space into an infinitesimally small point. There exists a fundamental, irreducible limit, a maximum possible density. Imagine, if you will, our universe contracting, much as it would in a great contraction scenario. It grows ever denser, ever hotter. But just as it approaches the point of becoming a singularity, a new force emerges, a quantum force. At this incredible Planckian density, gravity, the force we know so well as being exclusively attractive actually becomes repulsive. This quantum pressure pushes back powerfully and decisively against the crushing collapse. The universe does not crash into a singularity, it bounces. The immense kinetic energy of the collapse is converted into the explosive energy of a new expansion. The Great Contraction becomes the Great Bounce. Our Big Bang, then, was not a beginning from nothing, but rather a violent ricochet from a previous contracting cosmic phase. This idea is beautiful, because it elegantly circumvents the paradox of infinity. The universe never actually reaches a state of infinite density, and therefore the laws of physics are never truly broken. It is a continuous, albeit dramatic, transition from a collapsing prior universe to our own expanding one. We are living in the aftermath of a cosmic ricochet then. The Big Bounce invites us to envision a universe before ours, in some sense a mirror image, having fallen inwards for aeons, accumulating the potential that would be unleashed in the bounce that created our world. It is a universe that has a past, a history that stretches beyond the veil of the Big Bang, connected to our own by this moment of supreme quantum transition. Let us now swerve onto a less well-trodden path into the realm of deeper abstraction. Consider the idea of affine cosmology. This is a more radical rethinking of the fundamental nature of our universe itself. We are accustomed, to thinking of gravity, in the Einsteinian sense, as the curvature of space-time. Matter tells space-time how to bend, and the curvature of space-time tells matter how to move. It is a beautiful geometric dance. But what if that curvature isn't the most fundamental aspect of reality? What if it's merely a symptom, a manifestation of a deeper, more intricate geometric structure? This, at its heart, is what affine cosmology proposes. It suggests that the geometry of the universe is not based solely on distance and curvature, but on a more fundamental mathematical concept called affine connection. An affine connection is, essentially, a way of defining parallel lines on a curved surface. It is a more fundamental geometric tool. From this perspective, the Big Bang might not have been a singularity of infinite curvature, but rather a moment when the affine properties of the universe underwent a phase transition, much like water turning into ice. The universe didn't so much begin as it changed its fundamental geometric character. This is a deeply mathematical idea, and it is admittedly difficult to visualize, but it suggests that the questions we're asking about beginnings might be framed in the wrong language. We're asking about the beginning of space and time as we know them, governed by Einstein's theory. But perhaps there existed a proto-universe, governed by these more fundamental affine rules, a state where our familiar notions of gravity, space and time had not yet crystallized. The Big Bang was the moment of that crystallization. It is a profound reminder that our physical theories are models, maps of reality, and that a new map based on a different mathematical language might show that what we perceive as an edge, a beginning, is simply a feature of our old map, rather than a feature of the territory itself. It asks us to be humble about the very tools we use to describe existence, and to consider the possibility that beneath what we currently perceive might lie a deeper layer of mathematical reality, a reality where the very concept of beginning might not even hold any meaning. As we delve ever deeper into the realm of the truly strange, we leave behind the classical ideas of cycles and bounces and enter the world of quantum mechanics, where the rules of reality itself become fluid and probabilistic. Here, we encounter one of the most profound and mind-bending ideas ever conceived, the quantum birth of the universe from nothing. When we utter the word nothing in this context, it's not simply the emptiness of a vacuum, it is a state far more fundamental, a state utterly devoid of space, devoid of time, devoid of matter, and indeed, devoid of the very laws of physics. It is absolute non-being. How, then, could a universe brimming with complexity and energy possibly arise from this? The answer lies in the peculiar, almost whimsical nature of quantum fluctuations. Quantum mechanics tells us that even in a perfect vacuum, there is a seething background of energy. Particles and antiparticles can spontaneously pop into existence, exist for a fleeting moment, and then annihilate one another. This is the uncertainty principle at its most fundamental level. The idea of a universe from nothing suggests that the entire universe is simply a very large and a very long-lived quantum fluctuation. Two of the most well-known proposals in this area come from physicists James Hartle and Stephen Hawking, and from Alexander Vilenkin. The Hartle-Hawking no-boundary proposal is a particularly elegant, albeit abstract, vision. They suggest that if we attempt to journey backward in time towards the Big Bang, the very nature of time itself changes. As we approach the beginning, time becomes less and less like the familiar, forward-marching dimension we experience, and more like a dimension of space. At the beginning, there isn't a sharp point or an edge. Time smoothly transitions into a spatial dimension. Think of the surface of the Earth. If you travel north, you eventually reach the North Pole, but you cannot go north of the North Pole. There's no boundary there, no edge to fall off. The point itself is smooth and part of the surface. Hartle and Hawking propose that the beginning of the universe is akin to the North Pole of time. There is no moment before the Big Bang, just as there is no point north of the North Pole. The universe has no initial boundary, no beginning in the conventional sense. It simply is. It emerged from a purely geometrical, timeless Euclidean phase, a state described by imaginary numbers, into the physical, time-bound universe we inhabit, through a seamless quantum transition. There was no act of creation, merely a change in mathematical description. Alexander Vilenkin's model offers a slightly different, but no less stunning picture. He suggests that the universe sprang into existence through a process known as quantum tunneling. In the quantum world, a particle can do something classically impossible. It can tunnel through an insurmountable barrier. Vilenkin applied this concept to the universe as a whole. He envisioned the state of nothingness as being separated from the state of universe by an energy barrier. His calculations demonstrated that there is a non-zero probability that a tiny embryonic universe could spontaneously tunnel through this barrier, from a state of zero size and energy to a state of finite size and energy. It would simply pop into existence from nothing, just like a quantum particle. From this perspective, the Big Bang is the moment of this tunneling event. Prior to it, there was not only no space and no matter, but no time itself. The very notion of before is rendered meaningless. The reason for the universe's existence lies not in a preceding event, but in the timeless, probabilistic laws of quantum mechanics itself. Both of these models paint a picture of a self-creating universe, a cosmos that pulled itself into existence from the ultimate void, guided by the strange and beautiful logic of the quantum world. They suggest that the something of our universe is merely a different configuration of the ultimate nothing, a possibility that was always inherent within the quantum substratum of reality. Let us linger for a moment on this idea of a seething quantum reality at the heart of being. It leads us to the theory of quantum foam, a concept first proposed by the great physicist John Wheeler in 1955. He invited us to imagine peering down into the very structure of space-time at the tiniest, most fundamental level, the Planck scale, 100 billion times smaller than a proton. At this scale, he proposed, space-time is not smooth and tranquil. It is a turbulent, chaotic, bubbling foam. The uncertainty principle, which permits particles to pop in and out of existence, here applies to space and time themselves. Tiny bubbles of space-time, microscopic wormholes, and miniature fleeting universes are constantly fluctuating, appearing and disappearing, forming a boiling froth of quantum possibilities. It is a world of pure potential, where the very laws of cause and effect dissolve in a storm of probability. Could the entire universe, with all its galaxies and complexities, be nothing more than a supremely lucky bubble in an eternal seething primordial foam? According to this theory, our universe may have begun as one of these countless tiny bubbles within the quantum foam. For reasons we do not yet fully comprehend, one of these fluctuations, instead of vanishing again, was endowed with precisely the right properties to become stable and undergo a period of massive rapid expansion, what we refer to as cosmic inflation. This once successful bubble, born from the chaos of the foam, grew to become the immense structured cosmos we perceive today. The quantum foam hypothesis suggests that the state before our universe was not a single state of non-being, but an infinitely complex and dynamic state of everything, a realm of endless potential from which universes can spontaneously arise. It paints a picture of a pre-cosmic reality that is not empty and silent, but unimaginably violent and creative, a tumultuous ocean of potential from which the bubble of our reality ultimately emerged and found its quietude. Our entire cosmos, with its billions of galaxies and intricate laws, may be just one successful fluctuation in an eternal underlying quantum chaos. This idea decentralizes our own cosmic story, suggesting that the birth of a universe may not be a unique, special event, but a common, perhaps even inevitable outcome of the fundamental nature of reality itself. We have already touched upon loop quantum cosmology and its vision of the Big Bounce, where the grainy nature of space-time prevents a singularity. Let us delve into that fascinating picture a little deeper. Loop quantum gravity (LQG) theory proposes that space is not a continuous background, but a network of interconnected quantum loops. These loops are the fundamental atoms of space. One cannot have half a loop. One cannot have space smaller than one quantum of volume. Time, too, is discrete, ticking forward in tiny indivisible Planckian increments. Within this framework, the Big Bang singularity is simply impossible, an artifact of our outdated, continuous view of space-time. As the universe contracts, the loops of space are squeezed closer and closer together. The energy and density within each quantum of volume increase to an astronomical, but crucially finite maximum. When this limit, known as the Planck density, is reached, the quantum geometry of space-time itself exerts a powerful repulsive force. The atoms of space cannot be squeezed any further. The result is a bounce. This theory provides a detailed mathematical description of what happens at the moment of the Big Bang. It is not a beginning, but a bridge connecting a preceding, contracting universe to our own expanding one. LQG opens the door to the question of what that previous universe was like. Some models suggest it might have been very similar to our own, perhaps even an almost perfect mirror image. Others suggest that the bounce could be chaotic, randomizing the properties of the emerging universe. We may simply be living in one of a long sequence of such bounces, each with its own character. Loop quantum cosmology transforms the Big Bang from an absolute impenetrable wall into a window, albeit a hazy one, into a pre-existing cosmic era. It assures us that the history of the cosmos did not begin with our chapter, but that ours is merely the latest installment in a potentially infinite saga, written in the fundamental discrete language of quantum geometry. Our journey now leads us perhaps to the most expansive and dizzying territory of modern cosmology, to the concepts of inflation and the multiverse. These ideas suggest that our universe is not unique, but merely one of countless others. Let us begin with the idea of eternal inflation. Cosmic inflation is a theory originally developed by Alan Guth to explain some key features of our universe, such as its incredible flatness and uniformity. It posits that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated expansion, inflating from a subatomic size to something larger than a grapefruit almost instantaneously. The theory of eternal inflation, championed by physicists such as Andre Linde, takes this a significant step further. It argues that whilst inflation ceased in our region of space, allowing our universe to form, it did not cease everywhere. It continues eternally in the boundless reaches of a larger cosmos. Picture a vast, rapidly expanding ocean of inflationary energy. Within this ocean, pockets of space randomly drop out of the inflationary state, much like bubbles forming in boiling water. Each of these bubbles becomes a new pocket universe, with its own Big Bang, its own expansion, and its own future. Our entire observable universe, all the billions of galaxies we can perceive, is just one of these bubbles in an infinite, eternally inflating sea. This process is without end. New bubble universes are constantly being born from the inflating background, each one isolated from the others, expanding into its own separate realm of space-time. This creates what physicist Max Tegmark calls a level 2 multiverse. In this grand cosmic structure, our Big Bang was not the beginning, but merely a beginning, the beginning of our local pocket. The true before the Big Bang state from this perspective is the eternally inflating multiverse itself, a cosmic factory that churns out an infinite number of universes. Moreover, some theories suggest that the laws of physics might be different in each bubble. The constants of nature, the types of particles, the very forces that govern reality, could be set randomly each time a new bubble forms. We find ourselves in a universe with our specific laws simply because these are the laws that permit stars, planets, and ultimately, beings who can ask these questions to form, a concept known, of course, as the anthropic principle. But what if our universe is not just one of many, but one of an infinity of possibilities? This idea of multiple universes takes on a different form when we consider the strange rules of quantum mechanics itself. This leads to the Level 3 multiverse, also known as the many worlds interpretation. Proposed by Hugh Everett III in the 1950s, this theory offers a radical solution to the riddles of quantum measurement. In quantum mechanics, a particle can exist in a superposition of several states simultaneously. For instance, it could be in several places at once, but when we measure it, we always perceive it in only one state. The many worlds interpretation suggests that at the moment of measurement, the universe itself splits into multiple branches. In each branch, one of the possible outcomes is realized. If a particle could have been here or there, in one universe it is here, and in another, parallel universe, it is there. Both outcomes occur. All possible outcomes of every quantum event that has ever happened have been realized in some parallel reality. This branching process is happening continuously, everywhere, creating a dizzying, ever-expanding tree of parallel universes. This idea doesn't directly explain the origin of the first universe, but it entirely reframes the question of our own uniqueness. Every choice you could have made, every random event that could have gone differently, has played out in another world beyond the reach of our own. Before the Big Bang, from this viewpoint, there may have been a single quantum state, and the Big Bang itself was the first of an infinite series of branching points, creating the vast, layered multiverse in which we now reside. We are merely one leaf on an infinite tree of cosmic possibilities. This is not a multiverse of distant bubbles, but a multiverse of parallel streams of reality, coexisting in the same space, yet unable to interact. It suggests a reality far grander and more complex than we can ever perceive, where all stories are real and our lived experience is simply one path through an infinite garden of diverging pathways. Within the framework of inflationary cosmology, we also find the chaotic inflation model, again proposed by André Linde. This model addresses the initial conditions required to kickstart inflation. It suggests that in the very early universe, the quantum field responsible for driving inflation, the inflaton field, was not uniform. Instead, it was in a completely random, chaotic state, its value varying wildly from place to place. In some regions, the field's value was just right for inflation to begin. These regions expanded exponentially, smoothing themselves out and creating vast homogeneous patches that could eventually become universes much like our own. In other regions, the field's value was not suitable, and these areas did not inflate. Because the inflating regions grow to astronomically large sizes, they quickly come to dominate the volume of the entire cosmos. This model naturally leads to a multiverse picture. The chaotic initial state could give rise to countless inflating domains, each potentially evolving into a universe with different properties, depending on the local value of the inflaton field it started with. The before the Big Bang state is envisioned as a quantum chaos of fields, a churning sea of potential, where the conditions for creating a universe were met not by careful design, but by sheer chance in some fortunate corner of this primordial chaos. This idea removes the need for finely tuned initial conditions for our universe. In a chaotic multiverse, anything that can happen will happen, somewhere. We just happen to find ourselves in one of the regions where conditions were suitable for our existence. It paints a picture of our cosmic origin not as a precisely engineered event, but rather as a felicitous accident in a vast primordial storm of quantum fields. Our journey now brings us into the elegant, highly mathematical, and profoundly mysterious world of string theory, and its more complete version, M theory. These theories propose that the fundamental constituents of reality are not point-like particles, but tiny one-dimensional vibrating strings of energy. Different ways a string vibrates correspond to the different particles and forces we observe. For these theories to be mathematically consistent, they require the existence of additional spatial dimensions, beyond the three that we experience. In this higher dimensional reality, our three-dimensional universe might be a brane, short for membrane, floating within a higher dimensional space called the bulk. This opens up entirely new possibilities for what was before the Big Bang. One of the most prominent is the Ekpyrotic Universe model. The word ekpyrosis comes from an ancient Greek term meaning cosmic conflagration or rebirth. This model, first proposed by Paul Steinhardt and Neil Turok, suggests that our Big Bang was not a beginning from a singularity, but the result of the collision of two parallel branes in this higher dimensional space. Imagine our universe as a vast flat sheet. Another such sheet exists parallel to it, separated by a tiny gap in a fourth spatial dimension. For aeons, these two brane worlds might be empty, cold, and dark, slowly drifting towards each other through the bulk. The collision is the key event. When the two branes finally impact, the enormous kinetic energy of their crash is converted into the hot, dense soup of matter and radiation that we identify as the Big Bang. Our universe is born not from a point, but from the energetic meeting of two entire worlds. A variation on this theme is the cyclic ekpyrotic model, where the branes don't just collide once. After the collision, they bounce apart, drift away, and then, drawn by a force between them, slowly begin to approach each other again for a new collision, a new Big Bang. This creates an eternal cycle, similar to the oscillating universe, but driven by the dynamics of branes in higher dimensions, and crucially, it avoids the singularity and entropy problems of the older cyclic models. In this vision, the time before our Big Bang was a time of slow, quiet approach of our parent brane towards its twin, a long, silent cosmic winter before the fiery spring of the collision. The concept of brain cosmology extends beyond the ekpyrotic model. Randall-Sundrum models also describe our universe as a three-dimensional brane within a higher dimensional bulk. These models were developed to address the hierarchy problem, which is the question of why gravity is so much weaker than the other fundamental forces. In one model, there are two branes, a Planck brane, where gravity is strong, and a TV brane, where we live, and where standard model particles reside. The geometry of the fifth dimension between them is highly warped, which explains gravity's weakness on our brane. Another model simplifies this to a single brane in an infinite fifth dimension. The interactions of our brane with this bulk, or with other branes, could have profound consequences. Our Big Bang might have been triggered not by a direct collision, but by the gravitational influence of another brane passing nearby, or by some instability within the higher dimensional bulk itself. In these models, gravity is unique because, unlike the other forces, it is not confined to our brane. It can leak into the extra dimensions. This could explain why gravity is so much weaker than the other fundamental forces. Much of its strength is dissipated in the bulk. These ideas stretch our intuition to its absolute limit, asking us to imagine a reality where our entire cosmos is merely a sliver, a membrane, within a much larger unseen hyperspace. The state before the Big Bang would then be the state of the bulk and other branes within it. Our cosmic story is just one chapter in the broader history of this higher dimensional reality. This leads us to one of the most astonishing and controversial ideas to emerge from string theory, the string theory landscape. In the search for a single, unique version of string theory that would describe our universe, theorists discovered something unexpected. The theory, it seems, doesn't predict a single set of physical laws. Instead, it appears to allow for a colossal number of different possible solutions, each corresponding to a stable vacuum state, meaning each corresponds to a possible universe with its own distinct laws of physics. The estimated number of these solutions is famously enormous, often quoted as 10 to the power of 500, that's a 1 followed by 500 zeros, a number so vast that it utterly transcends any meaningful comprehension. Does the vastness of this cosmic potential diminish our own significance, or amplify the sheer improbable wonder of our particular existence? This collection of all possible universes is known as the string theory landscape. One can visualize it as a vast multi-dimensional terrain of valleys and mountains. Each valley represents a stable vacuum, a possible universe with a specific set of physical laws. Our universe is merely one of these valleys. This concept marries beautifully with the idea of eternal inflation. An eternally inflating multiverse could be the mechanism that populates the string theory landscape. As new bubble universes form, they randomly land in one of the many valleys of the landscape, inheriting that valley's physical laws. The state before our Big Bang would be the quantum foam of the landscape itself, a space of pure potential, where all 10 to the power of 500 possible types of universes exist as mathematical possibilities, awaiting an inflationary event to render one of them real. This theory suggests that the question, why does our universe have these particular laws, has a simple, albeit unsettling answer. Because in a landscape of 10 to the power of 500 possibilities, it had to have some laws, and we just happen to live in the one we do. It replaces the search for a single, elegant explanation with a statistical inevitability. Our universe isn't special. It's just one sample from an unimaginably vast cosmic warehouse of possibilities. Let us now plunge into the realm of truly exotic hypotheses, those lingering at the very fringe of physics and philosophy. These ideas challenge not only our concept of a beginning, but the very nature of reality itself. First, consider the simulation hypothesis. This idea, introduced into modern discourse by philosopher Nick Bostrom, suggests that our entire universe, including ourselves and all our memories, is a sophisticated computer simulation created by a more advanced civilization. The argument is a statistical one. Bostrom presents a trilemma. At least one of three propositions must be true. Firstly, civilizations like ours are very likely to go extinct before reaching a post-human stage capable of running such simulations. Secondly, post-human civilizations are extremely unlikely to want to run simulations of their ancestors. Or thirdly, we are almost certainly living in a computer simulation. The reasoning is that if civilizations do indeed reach a post-human stage and run many ancestor simulations, then the number of simulated minds like ours would vastly outnumber the number of original, biological minds. Therefore, statistically, it would be far more probable that we are one of the simulated minds, rather than one of the original ones. In this framework, the question, what was before the Big Bang, becomes, what was the state of the computer before the program was run? The Big Bang was simply the initialization of the model, the moment the cosmic enter key was pressed. The laws of physics are the lines of code that govern our simulated reality. The era before the Big Bang might not exist within the simulation's chronology, but the hardware, the programmers, and the reality they inhabit would exist outside our universe, on a higher level of being. It is an unfalsifiable hypothesis, meaning we currently cannot devise an experiment to prove or disprove it. It remains a profound and unsettling thought experiment, a cosmic solipsism that places our entire existence within the creation of another entity. Next, we encounter a strange and paradoxical idea, arising from thermodynamics and statistics, the concept of a Boltzmann universe, and its more famous relative, the Boltzmann Brain. This hypothesis springs from contemplating entropy and eternality. In an eternal universe that eventually reaches a state of maximum entropy, or heat death, a cold, sparse, uniform soup of particles, there is still a non-zero probability, given infinite time, for random fluctuations to occur. Given enough time, a truly colossal amount of time, it is statistically possible for particles to randomly assemble into a complex ordered structure. It is possible, for instance, for a fluctuation to create a new universe. However, it is statistically far more probable for a smaller, simpler ordered structure to pop into existence. For example, it is far, far more likely that a single conscious brain, complete with memories of a life it never lived, would spontaneously appear for a brief moment before dissolving back into chaos, than for an entire, vast, ordered universe to do so. This is the Boltzmann Brain paradox. If our universe arose from a random fluctuation in eternal heat equilibrium, then we should be Boltzmann brains. The fact that we find ourselves in a vast, old and highly structured universe is, therefore, a profound puzzle. Whilst not a popular theory of our own cosmic origin, it serves as an important sanity check for other cosmological models. Any theory of an eternal universe must explain why we are not these bizarre observers, why we perceive a consistent, ordered cosmos around us. It is a chilling, logical ghost that haunts the corridors of cosmology, reminding us that the most statistically probable reality might be a fleeting, solipsistic nightmare. Consider an even more fundamental reframing of the problem with the model of chronogenesis. We are so accustomed, to thinking of time as the fundamental river along which all events flow. We ask, what was before? But what if time itself is not fundamental? What if it is an emergent property, akin to the wetness of water, which arises from the collective behavior of H2O molecules, but is not a property of a single molecule? The Chronogenesis model proposes precisely this. It suggests that the universe arises from a more fundamental non-temporal state. This underlying reality is timeless. There is no before or after. There is only a complex quantum system existing in a static state of superposition. Time, as we know it, the forward-marching arrow from past to future, arises as a kind of phase transition in the evolution of this system. Imagine a perfectly still, frozen pond. This is the timeless primordial state. Then a process begins, a thawing, if you will, and a current begins to flow. This flow is what we experience as time. The Big Bang was not the beginning of existence, but the beginning of time. It was the moment of chronogenesis, the birth of the temporal dimension. Prior to it, there was no before, only a static, timeless reality described by a different set of rules. This idea is deeply abstract, but it elegantly dissolves the question of a first cause. You cannot ask what caused the Big Bang in a timeless state, because the very concept of causality requires time to function. The universe is not caused by a preceding event, but arises from a fundamental change in the very structure of reality, a shift from a timeless state to a temporal one. We find ourselves standing on the threshold of not just the known, but the knowable. But what does it truly mean to know when confronted by such boundless possibilities? In a similar vein, some thermodynamic models propose fascinating symmetries around the Big Bang. One such idea is the Ekpyrotic model. It suggests that the Big Bang was not a beginning, but a central point from which two universes emerged, running in opposite directions of time. Imagine the Big Bang as a point on a line. Our universe is the arrow of time moving to the right, away from that point, with entropy increasing as we move into the future. But this model suggests there is another universe, an anti-universe, represented by an arrow of time moving to the left, away from the same Big Bang. This mirror universe would also experience increasing entropy, but from its perspective, its future lies in the opposite temporal direction to ours. The two universes would be fundamentally linked, born from the same event, but forever separated by their opposing arrows of time. An observer in that universe would perceive our past as their future, and our future as their past. This idea is beautifully symmetric. It suggests that the total entropy of the combined system might be constant, and that the Big Bang itself was a special, low-entropy state that served as the common past for two symmetric, time-reversed cosmoses. The state before the Big Bang becomes meaningless. The Big Bang is the central shared moment of creation for two temporal streams. Our concluding explorations lead us through the most speculative and perhaps most cinematic of cosmic portals: wormholes, hyperspaces, and quantum tunnels. Let us first consider black hole cosmology. This theory, sometimes referred to as cosmological natural selection and championed by physicist Lee Smolin, proposes a profound connection between black holes and the birth of new universes. When a massive star collapses under its own gravity, it creates a black hole, a region of space-time with a singularity at its heart. The theory suggests that what happens at the heart of a black hole is not destruction into a point of infinite density, but the creation of a new daughter universe. The black hole singularity in the parent universe becomes the Big Bang of the daughter universe. Our universe, from this perspective, is the interior of a black hole that exists within another, parent universe. The matter that fell into that primordial black hole provided the energy and material for our own Big Bang. This creates a fascinating, almost evolutionary scenario. Universes whose physical laws favour the production of many massive stars, and consequently many black holes, will have more offspring. Over countless cosmic generations, universes with our particular set of laws, which are very good at making black holes, will become the most prevalent. This offers an explanation for the fine-tuning of our universe's constants, without resorting to the anthropic principle. We have the laws we have because they were successful in a cosmic evolutionary process. The time before our Big Bang was simply time in our parent universe, prior to the collapse of the star that became our cosmic seed. Another powerful idea is that of quantum tunneling from a metastable vacuum, also known as false vacuum decay. Imagine a quantum field that has several possible stable or semi-stable energy states, like a ball that can rest in several different valleys of a hilly landscape. The true vacuum is the lowest possible energy state, the deepest valley. A false vacuum is a higher energy valley, a state that is stable for a while, but it's not the absolute lowest energy state. The theory of false vacuum decay suggests that our universe may have begun as a bubble of true vacuum that formed within a larger pre-existing space that was in a false vacuum state. A quantum fluctuation could cause a small region of this false vacuum to tunnel through an energy barrier and decay into the lower energy true vacuum state. This bubble of true vacuum would then expand at the speed of light, converting the false vacuum around it into true vacuum. Our Big Bang would be the energetic event associated with the formation of this bubble. The state before the Big Bang was a different, other kind of universe, a false vacuum universe with, perhaps, other physical laws and properties, which was ultimately unstable. Our universe is the result of the decay of this previous cosmic state into a more stable one. This idea is a cornerstone of many inflationary and multiverse models, providing a physical mechanism for how a new universe with new properties could branch off from an older one. Finally, we return to a beautifully symmetric vision, the hypothesis of a CPT-Symmetric Universe. CPT stands for charge, parity and time, three fundamental symmetries in physics. A CPT transformation is like looking at a process in a mirror, parity, changing all particles to their antiparticles, charge, and running the process backward in time, time. A remarkable theorem states that the laws of physics are unchanged under this combined CPT transformation. The hypothesis extends this symmetry to the universe as a whole. It suggests that the universe on the other side of the Big Bang is a CPT mirror of our own. It is a universe composed of antimatter instead of matter, with spatially reflected coordinates, and with an arrow of time flowing in the opposite direction to ours. The Big Bang is the ultimate mirror. It is the single event that links our universe, expanding forward in time with an anti-universe, expanding backward in time. The overall state is perfectly symmetric. There is no preferred direction of time for the cosmos as a whole. The state before the Big Bang is, in essence, another universe, a perfect reflection of our own, evolving from the same point of origin, but in an opposite temporal direction. It is a vision of ultimate balance and harmony, where our existence is perfectly counterpoised by a mirror reality. As we drift towards the conclusion of our long and astonishing journey, allow these immense ideas to settle around you like soft, distant starlight. The steady-state universe, the cyclical universes, the big bounce, the universe from nothing, the quantum foam, the endless bubbles of eternal inflation, the layered realities of many worlds, the collisions of higher dimensional brains, the mind-boggling string theory landscape, the code of a simulated reality, the logical phantom of Boltzmann brains, the profound shift of chronogenesis, the mirror of a CPT-Symmetric cosmos, the cosmic genesis within a black hole, the decay from a false vacuum. It is crucial to remember as you float in this sea of concepts that all of these ideas are speculative. They are the grandest stories science can tell at its current frontier. Not a single one of them has been definitively proven. They are mathematical poems, philosophical explorations, built upon the bedrock of what we know and reaching out into the boundless expanse of what we do not know. Some of them address the question of a beginning by simply eliminating it, suggesting that the universe, in some form or another, has always existed. Others redefine the very meaning of beginning, transforming it from a singular event into a transition, a bounce, a branching, or a tunneling. Some even question whether time itself is a fundamental entity at all. There is no need to grasp them, to cling to their details, or to choose one over another. Their purpose this evening has been to expand the boundaries of your imagination, to show you the sheer intellectual audacity and creativity of the human mind when confronted by the ultimate mystery.